Okay, so let's start today's session talking about statistical learning theory. I think you have all handed your homework, so I will check them and I will ask Tam to correct them quickly. So if you remember what we did before last week, we mentioned classification, and so we insisted on the fact that classification and regression were related but different. So in the sense that the output space that we're trying to predict in classification is a discrete space. And we've discussed at length about binary classification, that is how we can provide algorithms that can decide for yes or no given an input. And we've spent a lot of time discussing linear classification tools. That is functions. So basically the part where we answer yes is the part where the dot product of x with the normal vector c is non-negative, and the part where we answer no is the part where the dot product of c plus b, is negative. So the big problem when you have to design a classifier is which technique you use, and we briefly discussed 4 of them here. So far in those 3 lectures, we have discussed both regression and classification. We have tried to give some theoretical ideas and motivations behind some of the tools. So if you remember, least squares regression was motivated somehow by the assumption that the observations were corrupted by some noise, which was Gaussian, etc., etc. But now today, we will really dig a bit deeper into theory, and we will try to answer a few fundamental questions when you apply machine learning algorithms. And let me just briefly define what is the standard timeline when you have to address a machine learning problem, when you have to use an algorithm. Probably you would have to define the problem itself. Do you want to classify objects? Do you want to regress them? Do you have a multi-class problem? So typically this is a problem that's given to you by a scientist, or by a social scientist, or by a company, an engineer. And you will help define better the problem, then gather the data. Then typically you would choose a representation of data to build a database. So you would build features, you will, define what kind of resolution you want your images to be, what kind of descriptors you want to use for those images or for those graphs, etc. And then you will choose a method or an algorithm, so one of those that we have mentioned so far. So you will have to choose between maybe a perceptron or a support vector machine or logistic regression or least squares regression if you want to do regression, lasso, forward, backward, etc., etc. Then you have to run the algorithm itself, choose the parameters. And then once you've reached that stage, usually this is the end of the story. And then you just give the algorithm to the person and tell that person, well, you can use it now. And if you have a new point that's coming, this will be the answer. But whenever you do that, you should always ask yourself if you have overfitted at some point the data. And we will try to give a definition now of what is overfitting and how this can be controlled, especially at those stages. That is, what kind of method or algorithm you want to choose and how you want to estimate the parameters of that algorithm. So to do that, we will use a probabilistic framework in the next lectures. So I will define it better because so far I was intentionally leaving it a bit not that clear. I wanted to focus more on the algorithms so that you have a better idea of mathematically how it works. But now we have to rely more on this probabilistic framework. So we assume that all the observations x, y that are in nature are split between x, this will be a vector, and y a set S. So S could be a real number or again labels, etc. So the problem is sometimes only x is visible. We want to guess the most likely y for that x. So we will use those two examples repeatedly in the next two lectures. So in the first lecture, we were using apartments and rents and surface and distance, etc., etc. Here we will be using those two examples. So the first one is assume you just sample from the population and then measure the height of a person and the gender. So you have two elements. And now you want to answer the question, given someone's height, what is that person likely to be? Is it male or female? So if person X is 164 centimeters, is X a male or more likely to be a female or a male? Same thing goes with now a real valued output, which is the weight. So we have the height and the weight. Given this person's height, this is the only information you have access to. What is the weight of that person? And you just want to do as well as possible. You want to be that guess to be as good as possible. So we will define what as good as possible means. So again, to estimate, to provide a guess, you need to provide a function. So this will be the problem. And the function will have to be good in two senses. First, it will have to be accurate on the points that we have observed in the training set, but also, and this is probably the most important, on the points that we will observe in the future. So to quantify this assumption, what we will do is that we will assume that all observations, each observation taken separately, arises as an independent and identically distributed random sample from the same probability law. So again, the independence assumption is the fact that one observation has no influence on the next one. So if I just take a coin and start drawing tails and faces and heads, the fact that I have drawn 20 heads in a row should not influence the fact that the 21st will be a head or a tail, right? There is absolutely no relationship, statistical relationship between the 20th draw and the 21st, okay? So this is the independence. And the identical distribution is the fact that if I have, for instance, if I have two coins, let's say they are asymmetric. This one has a high probability of having a tail, and this one has a high probability of having a head, okay? If I draw them separately, they are independent, right? They're completely independent. The fact that this is a head or a tail will not influence the fact that this is a head or a tail. But they will not be identically distributed, because as I told you, this one is more likely to have a head, and this one is more likely to have a tail because it's maybe bent a bit. The shape is a bit strange. So in that case, I can have independence, but not identical distribution, okay? So if you assume both independence and identical distribution, then you can work with a lot of the statistical learning theory framework. Again, those two are not equivalent, right? There are two different ideas. So we assume that all our observations are IID. So this is shortened as IID. So what we have is that we know that this exists. There is a probability which, if you want, governs the interactions between X and Y. Of course, if you have this probability here, you can also very easily compute the marginals, right? So here I say that I will use probability and density interchangeably, but those are two different things, right? The probability is usually defined on sets, whereas the density is defined on just one point, in the case where X is a continuous variable. So from this, of course, I can compute the marginals, what I call the marginals, which is, okay, I have two sets of variables, X and Y, and I can compute, I know what is the probability of having both at the same time, but this doesn't prevent me from knowing what is the probability of just having one of those observations. You just integrate over all possible values of X, and here you will integrate over all possible values of Y to get the other marginal. So the idea of the 10 or 20 next slides is that if So we assume that this exists, okay? That there's such a probability that's ruling the relationship. What would happen if we knew it, actually? So knowing that something exists and actually having access to it are two different things. What would happen if we knew it? I would like to convince you that if we knew exactly the probability, then all the problems that I've been talking about, classification, regression, etc., would become trivial. It would be like there's no point in even doing machine learning if we have access to the probability. Okay, so it's like running a marathon on a motorbike. It's pointless. It has no meaning. But since we never know it, well, we need to do without. But what would happen if we did? So suppose I know the probability for this particular problem, which is the height and gender problem. Okay. So having access to the probabilities means actually having access to this curve, right? The density. So this is male, this is female, and this is overall the probability of having an observation of a given height and a given gender in either two cases, and this heights are here. If I am considering the problem of height and weight, then knowing the probability is like knowing this shape, which gives me the density for each value of the height and each value of the weight of those of every human being on Earth. Basically, I could get his or her density here. So of course this should go a bit further because there are heavier people at 150, but this is plotted there. So let me just ask you just to check that you have elementary knowledge in probability. You all know, I think, the conditional probability formula, which is that for two events A and B to happen together, you can compute their probability of happening together as the probability of A happening knowing that B has happened times the probability of B itself. Okay? So suppose I'm telling you the height of a person is 184, the probability that the height of a person is 184 centimeters and his or her gender is male, well, this density, 0.015, and I'm also telling you that the overall probability of having a person which is a male is 0.5. So in that case, what is the conditional probability that the person's height is 184 if I have told you that the person's gender is male? So let me just. So again, I'm just asking you to compute this. It should be easy. Actually, this is not bad. This makes it easier. Makes it easier for me to stop. Okay. Okay, so I think most of you have answered right. So it's 0.03. So why was 4 so misleading? Okay, because some people probably divided by 2. So the thing is, it's just that so this formula applies for probabilities and densities. It's the same thing. So it's here we just want to know the probability of x equals 184 knowing y. So it's probability of A knowing B. And the probability of A knowing B is just simply the probability of AB divided by the probability of B, right? And here the probability of AB is 0.015 divided by 0.5. So that's the same thing as multiplied by 2. So it's 0.03. Now, again, this will be a very quick check. Bayes' rule. The probability of A knowing B is equal to the probability of B knowing A times probability of A divided by probability of B. So that's, if you forget Bayes' rule, it's trivial to remember. You just rewrite what I just wrote in both possible directions. Okay, so we have just simply that. So which direction did I put it here? Yeah. We just have the probability A knowing B times probability of B is equal to the probability of B knowing A times probability of A. So you just take this and put it here. Okay? So now we just computed this. Probability that X equals 184, knowing the person is a male, is 0.03. Probability of Y equals M is still 1/2. Probability of X equals 184 is 0.02. What is the probability that the person is a male if I know the gender? Sorry, what is the probability that the person is a male if I know the height? Okay, perfect. So yes, indeed, the question is if you just apply this formula directly, then you will get 0.03 divided by 0.02 here, and then multiplied by 0.5. So you have 3 halves multiplied by 1/2. So it's 3/4 and it's 0.75. So of course we will use a lot of this. And so let's simply just move on with what comes next. So statistical learning theory builds upon making mistakes, the idea of making mistakes and judging how big mistakes are, which is why loss functions are really fundamental. So we've seen quite a few loss functions so far, so let me just tell you again what it is. It's just a loss is a function that goes from S to RD, so the output times the input. So I forgot a D here. And which is a non-negative function designed to quantify mistakes. So how good is the prediction of f of x given that the true answer is y might be formulated as how small is the loss of y given f of x. So if S is just the binary, the set of 0 1s, then we have mentioned a bit the 0 1 loss, which is just a loss of 1 if there's a mistake and 0 if not. If the output is R, then you can use the Euclidean distance between the two answers or any other form of norm. So that's the first block. The second one is the risk, basically. So from that loss, we can define what we call a risk. So the risk of a predictor, so here predictor is not exactly the way I was using it in regression, but the risk of a function, if you want, of an answer, f with respect to loss L, is the expectation with respect to the probability, P, of the pairs of the loss of y f of x. So it's basically looking at every pair x, y that exists, checking whether my function f is right, and how wrong it is given to me by this loss, and then weighting this mistake by the probability, and then summing this over the whole space of possible answers and input and outputs. So the risk is the average loss of f on all possible couples. And here average is very important. The idea is that the probability here plays a key role. So here is a very important remark that you should make, is that a function f with very low risk can make very big mistakes for some x as long as the probability p of that x is small, basically. So if you have a regression function which needs to be trained on a set of x and y's, for instance, so if you want to predict the weight of someone given its height, if your prediction for a person that is 250 centimeters is like 10 tons, it would very likely have a very, very small impact on the risk of that function. Why? Because basically there's so few people that weigh 250 centimeters that it will make a very, very small mistake on average. However, if your function makes lots of mistakes in the range of 170 centimeters, then this will have a very big impact on the risk of your function. So again, we will use risk as the standard to define whether a function, the predictor here, is good or not. Okay? And to define risk, we need to define a loss. Okay? So risk equals two things, probability and loss. Okay? Loss we define ourselves, probability we assume that it exists, and this gives us the risk. Okay? So this is all a bit optimistic because I'm defining an object that I cannot compute. Okay? I just want you to have this clearly in mind. In practice, I will not be able to compute the risk because we never have access to probability. Okay? But ideally, if we had access to probability, which I will be assuming for a little now, well, this would be really what we want to minimize. This is something that we want to be small. We want f to make as little mistakes as possible, especially on average. Okay? So what can we say about the risk? Well, there's the first thing that we can say, which is very simple, is that the loss here, we said that the loss was non-negative valued. Okay? And we said that the risk was the average loss over all possible values of x and y. Well, this makes the risk of any function a non-negative quantity, right? This cannot be negative. So if you consider the set of all possible functions that go from Rd to S, the set of all input-output maps, then you can write something as the infimum, the smallest risk for all functions in that space. So if you, in mathematics, when you consider this kind of space here, the set of all possible functions from Rd to S, then you're bound to have very, very strange looking functions. Really, really weird, not regular, not smooth functions. Well, if you take the minimum over all that set of functions, you will get something called the base risk. Again, there is a minimum because the risk is lower bounded here, right? So there must be a value which is the infimum. And that infimum is itself non-negative. So R star is the infimum for all functions of the risk of f. And this is really what we want, actually. Ideally, if you care about the task that you have at hand, you want to find a function which has the lowest possible risk, and if it's the lowest as possible, then we call this the Bayes risk. Okay? So Bayes name is used in different contexts. So we have Bayes rule, you have Bayesian statistics, you have Bayes appears everywhere. Here, the only reason why we call it Bayes is that because we assume that we know the probability of x and y. Okay? And we will see that if we know that, we can do something quite nice, which is that we can actually give an explicit formulation for the Bayes risk, for the Bayes for a classifier that achieves the Bayes risk, and that classifier is called the Bayes classifier. So let me just define this. So let's write eta of x. Okay. Is the probability, so I'm sorry, I should read the title. Assume that we are in this case, okay, the binary classification case. Assume that we are using the 0-1 loss, okay? I pay a price of 1 when I make a mistake and 0 when I'm right, okay? So now that I have defined the loss and S, I can also define the risk, right? So let's write eta of x is the probability that y equals 1, knowing that x equals x. Okay? So this is the conditional probability. And let's define the following rule. I call this fb of x. So fb of x is very simple. It will tell you that the answer is 1 if eta of x is bigger than 1/2 and 0 otherwise. Okay? So it's if you really look into this formula, it's very intuitive. The Bayes classifier will say that x is 1 if the probability that it's a 1 is bigger than 1/2, which means that the probability is a 0 will be smaller than 1/2. Okay? Then if you define the Bayes classifier this way, then we can show that the Bayes classifier achieves the Bayes risk. Okay? Meaning that it has the best possible risk, the lowest possible risk. Okay? So the proof is a bit lengthy, but let's do it. So the first thing that we will show is that for any g, like this, we'll show that R of G is bigger than R of FB. Okay? This is the result we want to prove. And this, if this is true, this means that FB, the Bayesian classifier, the Bayes classifier, achieves the Bayes risk, right? I think you agree with me on this one. So R, remember that R of G minus R of FB is equal to the integral of the loss. So it's going to be just simply 1 J of X different from Y minus 1 FB of X different from Y, P xy dx dy. Okay? So now we can condition on X maybe I should probably follow this. Probability. Okay, maybe this is a bit too long. I think it's probably going to be easier if I just read it out loud with you. So the risk of G minus the risk of F star is equal to, if you use the 0-1 loss, this is not a trivial statement, but it's just because you're using the 0-1 loss. It's equal, the risk of G is equal to the probability of G of X different from Y. And the risk of F star is equal to the probability of F star of X different of Y. Now, if you condition by X, so we're going to sum that probability over all possible values of X weighted by the marginal probability of X here. So what we want to show this is non-negative, right? And if you can show that the integrand, that is this part, is itself non-negative, then the integral itself will be non-negative, okay? So what you can do to prove that this is non-negative, you can prove that only this part here is non-negative. And so this is what you can try to prove here. So basically this integrand, we only need to prove that it's non-negative here. To do that, well, it's a bit tedious, but first you give an explicit formulation of this quantity here in terms of eta and an indicator variable of g of x. So let me just go through this. So the probability of g of x is not equal to y, knowing that x is equal to x. It's just 1 minus the probability that they are equal, given x equals x. Now, what you just do is that you will split two cases. If y equals g of x, then it's either y equals g of x equals 1 or y equals g of x equals 0. So it's those two terms here. Those two probabilities can be written as expectations of indicator functions. The probability of something is the same thing as the expectation of the indicator function of this happening. So the probability of this is the same thing as expectation of 1 y equals 1 g of x equals 1, knowing that x equals x. The same thing applies here for the 0 case. Now, if you look at this expectation here, there is only this part which is random. This part here is not random because we know already what the value of x is. Okay, so basically this here is just simply 1 g of small x equals 1, so it goes outside of the expectation. The same thing happens here. And so now we're going to turn this again into a probability. Again, the expectation of 1 y equals 1 knowing x equals x. This expectation of the indicator function of this is just the probability that y equals 1 knowing x equals x. Okay? And this quantity, we know it as eta of x. Okay? The same thing can be done here. This quantity here is just simply 1 minus eta of x. Okay? So this is a long way to write that the probability that g of x is not equal to y when you know the value of x is basically 1 minus eta of x if g of x equals 1, 1 minus eta of x if g of x equals 0. Okay? So now we have computed this quantity just for one function g. We can take the difference for g and for f star. F star is fb, is the Bayesian Bayes classifier. So if you take this minus this here, then you have those two ones which cancel out, and then this part here will appear first for f of x star or f of xb, plus the same part for g of x. here. Then if you just group terms and the fact that, okay, if f, let's use it for if j of x is equals 0, 1 of j of x is equals to 0 is equal to 1 minus 1 g of x is equal to 1. So you can just modify this into only indicator functions here which depend on whether g of x and f of x is equal to 1, and here the same thing. And so in the end, this is a bit long, but what the expression that you get for the integrand is this. It's 2 times eta of x minus 1 times this difference. Okay? So what we need to show is that this quantity here is always non-negative. Okay? If we can show that this is non-negative, this is non-negative, this part here is non-negative, the integral is non-negative, so this is non-negative, so r of g will always be bigger than r of f star of r of fb. So you can do this simply by just recalling that if you have an x such that eta of x is bigger than 1/2, then this term is non-negative. Since this now is equal to 1, because by definition if eta of x is bigger than 1/2, f, the base classifier, will output 1, so this is 1. And this can only be 0 or 1, so this is non-negative. So non-negative type is non-negative is non-negative. If on the other hand eta of x is smaller than 1/2, this is negative. This can only be 0, because the base classifier will output a 0. And this, again, can only be minus 0 or minus 1. So this is this is negative 2. Okay? So in both cases, we have that the integrand here is non-negative, which when you sum it up with respect to, when you use the integrand here is non-negative, so when you sum it up you get a non-negative quantity. So basically, if you know the probability, you can compute this p of y equals 1 knowing x equals x. So we can compute the conditional probability. And this is enough to give you the best possible classifier. Okay? So if you want to play with the curves that I just gave you, how can you actually compute this eta given these two curves here? Okay? So this is I told you that if you have the density, then you have function eta. And this function eta is all you need to compute the best possible classifier. Well, to really compute the function eta, you need to do a bit of Bayesian calculus, very elementary. Again, the chain rule of conditional probabilities, Bayes rule. So a simple way to compute eta is the probability of y equals 1 knowing x equals x. So if you just use this, you get this ratio, the probability of y equals 1 and x equals x divided by the probability of x equals x. Using again this rule, you can condition again on y, and you get probability of x equals x knowing y equals 1, etc. And then the probability of x equals x can be conditioned on both probability of y equals 1 and y equals 0. So I'm just writing this because if your curve were initially those two ones, male density and the female density, and then you have the prior probability of y equals 1 and prior probability of y equals 0, then you can compute this curve. So if you check the scripts that are online for this lecture, you will see how you can compute this curve using only those densities. Now it becomes clear when you should say that someone is a male or a female. Okay? Whenever the height of a person would be above 170, maybe, then you can say the person is a male or female. Of course, this is completely irrelevant if you take into account the whole world population, right? It doesn't make a lot of sense. So in this case, I think the data was not sampled IID on the world. The whole data came from a database in the US. So since height in the US is significantly higher on average than in the rest of the world, then this is a bit biased towards the US. But this, anyway, if you have access to what I want to say is that if you have access to a real probability, then you can always compute this function eta of x, which will give you the best possible result. Now the other case of regression is also handled in a very similar way. Suppose that the output is a set of real numbers, and suppose that the loss is the 2 norm, okay, the least squares. So here's an additional reason why it's interesting to use the regression setting of orthogonal least squares. In that case, the Bayes, it's not a classifier, but the Bayes regressor is to say, if I have access to a probability, and then you give me the value of x, then the best possible answer with that loss, the f with the lowest risk with that loss, is the conditional expectation of y given x equals x. And that would be this quantity. So here again, you can prove that the Bayes estimator achieves the Bayes risk. That you cannot do better than predict with the conditional expectation. So again, if you had using Bayes rules, again, you could come up with an expression which depends on whichever information you have been given. So for instance, if someone gave you the conditional distribution in the other direction, then you could easily come up with the function f star. So what happens in practice? In practice, none of this happens. We never have the probability. We never have the real probability p. So everything that I've been discussing so far is more is basically fiction. What happens in practice is that you only have access to finite samples. So again, if we knew p, then we cannot beat Bayes estimator, but we never know p. In practice, the only thing that we have is a training set. It's just observation. We can have a very large number of observations, but that's the only thing that we have access to. So in the case of the height and gender problem, this would mean that someone would give you just a very long database of height and gender. Actually, if you look at the scripts, this is how I computed my fictitious probability density. Those curves here were not given to me by anyone. I just did density estimation using a database and then plugged those into the tools that I had. So again, for any function, we cannot compute its true risk, the expectation, etc. But what we can consider is something called the empirical risk. So the empirical risk is just the average of the loss. So it's the same loss here, but it's averaged over data points that appear in your training set. Okay. So the law of large numbers tells us that for any given f, if I give you one function f, this will converge to this as n goes to infinity. For this law of large number to apply, what is needed? What is exactly needed? IID? Yes, I think someone maybe said that. IID-ness. Basically, the data has to be IID. Otherwise, it will not work. Okay? So hence one of the reasons why it's important to have IID data. So when you have IID data, if you start sampling 1 million, 10 million, 100 million points, then this will start converging to this in many different senses. There are strong and low and weaker forms of the law of large numbers, and both can apply. So as size grows, the empirical behaves like the real risk, the true risk. So it might seem like a good idea to minimize directly the empirical risk. So what we want, again, we want to have as little risk as possible. We can never compute that risk. Instead, we have is finite samples. We can compute an empirical risk with that. This converges, when n goes to infinity, to a true risk. So it sounds like a reasonable idea to minimize this thing, which converges to the real risk somehow. So the intuition is that since it's good that R of f is low, since the empirical risk converges to the real risk with n going to infinity, if we have, let's say, 10,000 points, maybe it's a good idea to minimize the empirical risk directly. So if you're using classification with a 0-1 loss, you would say, let's find a function f which has very low empirical loss. Okay? However, this intuition is flawed. There are a few problems that can arise from this intuition, and many things can go wrong. And let me just give you one very simple example. So suppose someone gave you the database which is x1, y1, x2, y2, etc., xn, yn. And you're dealing with a classification problem. Okay? So I will now that you have given me this database, so people might call this overfit, this database, but you could also very simply think of it as memorizing the database. You create a function h, which very stupidly answers all of the data that you gave me so far. That is, if x equals x1, well, you told me it was y1, so it's y1. If x equals x2, you told me it was y2, so it's y2, etc., etc. And you do this for every single point on the database. You scan the whole database, and if you don't find the point, this new point here in the database, you just answer 0. Okay? So it's very easy to see that the empirical loss of this function here is 0. Right? If you just give me a database, I learn it by heart. That is, I just memorize the answer for each of the points that you gave me, and then completely forget the rest, then at least on the database that you gave me, I will make 0 mistakes. Okay? Of course, I will make 0 mistakes on the answers that you gave me before, but it's very likely that I will make a lot of mistakes on new points that will appear because they were not in the database to start with. So since I will always say 0 whatever the new point that you give me, then it's very likely that I will make a lot of mistakes. And actually, if you just compute the risk of that function h on the true risk of the function h, then you will get the probability of y equals 1. So let me just give you the example. Someone gives me a few observations of height, people's height. Some of them are male, some of them are female. So I would say that female here is 0 and male here is 1. Here is the function that I propose. It just tells 1 for a few very specific heights, which are the ones that you gave me in the database, and says 0 everywhere else. Okay? So the empirical loss of this, the empirical risk of this function is 0, but it will always make a mistake for someone who's a male. I will always, except if you except if you fall into one of those numbers here which have been defined before. But that's very unlikely if the data is really very accurate and hasn't been rounded. So here, just with this very simple example, I've shown that minimizing the empirical risk and doing only so is not a good idea. It's not enough. Because you can very easily fall into traps, and that's something we really want to avoid. So here are a few ideas to avoid overfitting, and we're going to discuss them in detail. So why intuitively is the approach which I just described bound to fail? The idea that I give you a finite set of points and you learn a function from that set of points, having only in mind the fact that you want to minimize the risk. Well, in 2 lines, the intuition behind is this. Our criterion here considers a finite set of points. There's only, even if it's 10 million or 100 million, it's still a finite set of points. On the other hand, if you allow yourself to find the function g in a set of functions, then you have to provide values for an infinite set of points. And you have too many degrees of freedom to choose the function. So the fact that the database is finite, and on the other hand, the function g can be potentially defined by an infinite number of values, makes things go wrong. So you need to add some kind of regularity. So to control overfitting, the first approach which we will discuss is to restrict the set of candidates. That is, instead of looking for a function g that is in a set of functions in a very broad sense, we will say we want the function to be linear, to be quadratic, to be of this sort, etc. And the other one is penalized approaches. So here I'm telling you that those are 2 good ideas, but why exactly? So this is the answer we will try to provide. Are there theoretical tools which can justify these ideas? So the most basic tool to do that are called bounds, basically, learning bounds. So we will build on those 2 assumptions again. There is a probability and the sample is IID. Then we assume that somehow we will always do something of this sort. Get a random training sample, assume that the data is AID, choose a class of functions G, method or this is basically choosing a method or a model, and then choose a function G of n in that class of functions G, such that the empirical risk of G of n is low. And actually I've hinted that this was easy, but actually it's quite hard and can be very, very hard. Even if you're just minimizing a criterion defined on a finite set of points, sometimes it can be very difficult to find the best function within the class of functions G which minimizes that criteria. So this is just for notations. The data set is of size n. The set of functions is G. And I will try to look for a function Gn which minimizes this. It might be an exact minimization or approximate minimization. So what are the questions that you might want to ask in that case? At least a partial answer. So if you take a function Gn, this is your answer. Maybe you would like to know how good you could have actually performed if you really had access to the real probability? So that's an important question. For instance, sometimes you will run an algorithm on the problem which seems very hard to learn. Sometimes problems are really difficult. So for instance, the height and gender problem is inherently difficult. You will make a lot of mistakes if, for instance, the person's height is 165 centimeters. It's very difficult, very likely that you make a lot of mistakes. So even the Bayes error in that case is quite high. For some other problems, actually, the Bayes error could have been much lower than what you have you actually achieve with your function. The other thing is we compute Gn using the empirical risk. Okay, so the empirical risk is the criterion that we use to compute this. What about the real risk of Gn? So this is another very important question. Maybe let me just think if I should do this. Okay. So here is a picture. See, this is the space of all functions that go from Rd to S. Okay? We know that there is a risk functional. Which is this function R, which tells us basically what is the value of the risk of a function f. And this relies, always remember that this relies on the loss and on the probability. Okay? We know that this risk is minimal for some function. And we call this the Bayes decision. So this point here would be f star or fb. Okay? And remember that this here is just a value. So this is necessarily bigger than 0 here. And this we have called R star, okay, the Bayes risk. So what happens in practice is you never see this blue curve, right? What you see instead is a function which is called the empirical risk, and which depends on endpoints. You can take the minimum of this empirical risk, but what we also do is we never really, let me just, usually we never really have access to this, the minimum of this function here either. Because we're always looking for functions in the class of functions G. So the minimum of this would be Gn. Or at least Gn is not too far from that minimum. This is what we're assuming. Okay? So there's many things that you can now do. from here, this is what we would really like to have if we had access to full information. To here, this is what our algorithm outputs. Okay? And this is what our algorithm outputs because we never really optimize on the set of all functions because we said that this would be a problem. We always restrict ourselves to this set G. And we cannot optimize with respect to the blue curve because we don't have access to it. So it's a bit annoying. We would like to be here, but this is the best we can do. However, what we can try to do is measure how far we are from this function. So we're not going to measure the distance from here to here, because that would be very difficult. What we will do instead is compare a few things. So the first thing that we might want to do is, what about this difference? Okay? This is quite a big difference. I believe my empirical risk is low, and I have minimized empirical risk hoping that this would mean I would have a low real risk. But actually, this is not really happening here. The real risk of my classifier here is quite far from this, the real risk of the best possible classifier. So if you want, here, this is this question. What about the real risk of Gn? And this question here is basically this distance. What is the difference between the real risk of the base risk, the best possible risk, and the risk of my answer, my Gn? Okay? So here is another important question, actually, which I didn't even consider here in this drawing. Sometimes it's actually very difficult to get here to this Gn. So we know that the best possible point in that class is Gn. The best possible empirical risk is minimized here. But sometimes, actually, the best that you will be able to do is not really get here, is maybe get here. So in that case, what you would be comparing is the difference between the best and what you have obtained. Okay, sorry, this is a different thing actually. This is even another thing. It's the difference between the empirical risk of Gn. No, that's good. That's what I want to say. Yeah. Okay. This is well, this is the same thing. So there are many questions that we might want to have an answer to when we do this. Because we're blind and we don't know any of those informations, doesn't mean that we cannot try at least to have a small guess. And this is the idea of statistical learning theory. So if you really look at the problem of estimating all those functions, it's very likely that the base risk, so the base classifier, the base decision, will not be in G. Okay? So for instance, if you use, let's say that you use linear regression to estimate the relationship between the height and the weight. Okay? It's very likely that the real relationship between height and weight, the best regressor, which will tell you the weight of someone based on his or her height, is not a linear function. Okay? So this is the meaning, this is what in this example, It will not be a linear function, but we can still try to use linear functions. So what people usually do is that they split the gap between this and this by simply saying that instead of focusing only on the base function, the base decision, we might instead focus on the best function in the function class G, which minimizes the risk. So in this case, this would be the G star, sorry, this is a different G star. Let's call it a G star like this. We'll remove this. So the function here which has the lowest risk in my function class G is this function here, right? It's G star here. So somehow, if you decide that you will restrict yourself to a certain function class G, what could be the best possible answer in that function class G? So that's called G star. So when you will split, when you will measure basically how far this is from this in terms of errors in risk, what you can do is split this difference into two terms. So here I'm just removing R of G star and adding R of G star. And then say that this difference here is just this plus this. And we call this first term here the estimation error. And the second term here the approximation error. Okay? So no matter what happens, if I define a function class G, this will never change, right? No matter what the type of data set that I have, the size and number of points, the difference between this and the best possible in the function class G here, this doesn't depend on the database. Okay, so this will always exist. So this is called approximation error. It's called approximation in the sense that we are approximating functions using a computer. So we need to restrict ourselves to functions that we can compute. So typically, I mean, linear functions, exponentials, etc. They have to be part of the arithmetic that a computer can carry out. So this is called the approximation. The one part which is more interesting, actually, is the estimation error. Why? Because this part actually depends implicitly on the number of points. You can expect that if n, the number of points n goes to infinity, then Gn will converge to G star. And that's the best that we can do. Okay? This doesn't depend on the number of points. This depends on the number of points, and this is what we really want to measure, actually. Okay? So this is why we will focus on the estimation error. So what do we call error bounds? So an error bound is basically to say that the real error of Gn, we can prove that it's below the empirical error of Gn plus some value here. Okay. So this is, it's not necessarily intuitive at first, but it's really, really important. Again, here I have my class of function G. This is the real risk. this is the empirical risk. What I'm saying is that if I minimize here and I get G of n, what is really problematic actually? Is it the case where so concretely, if you come up with a function whose empirical risk is higher than the true risk, is it a problem? If, for instance, you compute a regression function, okay, using a finite database, you have computed this function. And then it turns out, because you know it, someone tells you, that the empirical risk that you have computed on that database is smaller than the true risk. Is it a problem? Is it an overfitting problem? It's not an overfitting problem, because basically you expect that your function which will make a certain amount of errors, but it turns out that in practice, not in practice, but if you knew exactly the probability, you will make even slightly less errors. So the problem of overfitting appears in the other direction. The problem of overfitting appears when you think that because your empirical risk is low, the true risk will be low. Okay? So to control overfitting, what you can do is provide a bound. You will say, so again, this case, empirical risk higher than the true risk is not a problem. This is really not a problem. Because you think, according to your calculations, you're making 20% error, and actually maybe you were lucky. Actually, in real, if you take the whole probability, etc., you make 18% error. Okay? The problem is this one, and actually I'm writing these arrows in this direction. The problem is overfitting is when you are minimizing the empirical risk, you get a zero value for the empirical risk, and the true risk is actually much higher. Okay? So what you can do to control this is, I should have what you can do to control this if you can, is to sandwich the true risk below some value which will depend on n and maybe the function class g. So again, let's talk in percents. This is the error. So this is 1. Basically, I'm always making mistakes. I get everything wrong. And 0, I'm always right. Overfitting happens when you do this. The empirical error of your classifier or regression function is very low. And actually, the true risk of Gn is very, very high. So this is a disaster. Okay? This is really bad. If you use an algorithm that never takes into account this trade-off, this will happen very often. You will run your algorithm, you will find a low empirical error, and you will be very optimistic about what will happen in the following. And maybe, I'm just saying this maybe because we cannot compute it, but actually what happens is that the true risk of the algorithm is very high. So what you can try to do is this, and this is really useful. You can come up with a theory which tells you that the true risk lies somewhere between here and the empirical risk plus a quantity which depends on n and on g. And this, ideally, this c constant, which depends on n and on g, will go lower and lower and lower. Will become close to 0 when n goes to infinity. Okay? So that's the objective of statistical learning theory. It's to provide a bound. I mean, that's not the only one, but it's one of the objectives, is to provide bounds of this sort. Of course, these bounds cannot always be provided. They depend explicitly on g. Okay? Typically, if g is the set of all possible functions, as I showed you in the previous example, then it's very easy to construct functions that don't work. But if g has some characteristics and n is big enough, etc., then we can do things. There are other types of bounds which you can consider. Typically, one of them is called the error bounds related to the best in the class. So instead of only focusing on Gn, we can also focus on how far from the best possible function g in calligraphic g can I get, and is there a way to guarantee that the real risk of Gn, again Gn is computed using empirical risk, but here the real risk of Gn would be still lower than the risk of G star plus some constant, which depends again on n and G star. And this is probably the best possible thing that you can compute. The error bound relative to the base risk. Imagine that I tell you that I give you an algorithm whose risk, the real risk of g of n, of the algorithm, is smaller than the real risk of the best possible risk function, so the base risk, plus some constant which depends on n and on g, which would decrease very quickly with n being big. Okay? So I hope you understand the intuition behind the theory. The theory is not just an exercise in mathematics. It's trying to provide answers for people who run algorithms, g of n, and those answers take the form of those bounds here. They're somehow guarantees. So sometimes those bounds are very loose. So for instance, this c here, those c here are so big that they're just saying something like this. They're just saying, okay, the real risk is somewhere here. And in that case, statistical learning theory is useless, because it's just telling you something that you already knew, which is that the true risk is below 100%. Okay? In that case, that would be very, very stupid. So sometimes some of the theories don't necessarily make practical sense. But if n is big enough, etc., then you can find interesting quantities. So we will focus on error bounds, which are also called generalization bounds. So the generalization bound, again, is the difference between, is bounding the difference between the real risk of Gn and the empirical risk of Gn. So again, this drawing. Okay? So overfitting is the idea that given n training points sampled randomly, given a function Gn estimated from this point, we might have that the empirical risk grossly underestimates the real risk of Gn. Okay? So it's a very tricky thing, because the way we compute Gn is by minimizing this. Okay? the way we compute the function gn is by minimizing the empirical risk. But in doing so, we might miss the fact that actually the real risk of gn is much bigger. So one of the important questions that are studied in those theory of bounds is, what is the probability that the risk of gn is higher than the empirical risk of gn by a factor of epsilon? Okay. Basically, if epsilon is quite big, if this probability is large, then it's really bad. So from now on, we will consider the classification case, which is easier to study than the regression case. So all the functions that we will talk about are functions of the type that goes from Rd to 0, 1. Okay. So here I'm just laying the foundations for next week's lecture. So I just want to clarify some notations. So I told you that every observation in itself is a realization from a random variable. And that random variable can be split between x and y. Okay. So for notation purposes, it's a bit lighter actually to write this couple x, y as zi, as z, just as one z. So each observation will be zi, xi, yi, and the space of x and y's is just better. Sorry, the random variable, the joint variable xy is better written as big Z. Because we are only considering the binary classification case, and the only thing that matters is the loss of binary classification, and the loss that we have using is the binary loss, 0, 1 loss, we will consider a set of functions called the loss class, which to a couple Z, x, y, just gives the value 1 or 0, whether g of x is equal to y or not, for all possible functions g. Okay? So this, if you take all possible function g's, this defines a set of function f's, which are valued on z, which takes as input z, and as output just 1 or 0. So why am I using those notations which are a bit heavier? Well, because I just want to highlight the fact that the loss of a function g can be just simply seen as the probability applied on f, that is just the expectation of this function f, and that the empirical loss of g, of the function g, is just simply an empirical operator applied on f. Okay? So from now on, it's a bit easier to write the empirical loss of g just simply as this operator Pn of f. The operator being just simply I'm computing the value of f at n points xi, yi. Okay? And this, you can very easily see that this corresponds to the loss of the function g. And P of f, instead of being an empirical operator, it's a real operator. It's a true probability. So it's just the expectation of f of xi. So maybe you're familiar with those notations, but I just want to write them again. So you can easily see that Pf is just the empirical risk of the true risk of g. Okay? Pf true risk, Pn of f empirical risk. So for each function f, Pn of f is a random variable which depends on n realizations of z. Okay? So this is probably one of the most important remarks that we need to make. In this context, randomness comes from the sample. Okay? We assume that each sample is a random sample. If I ask any of you to collect some data about the height and gender problem in Kyoto, I will have, I don't know, maybe you're 18 in the class, I will have 18 different samples. Okay? So the randomness comes from each sample. Each sample is a different realization of an IID probability there, sampled many times. And so this is where the probabilistic aspect will come from. Here, when I'm writing a probability which is computed from n samples, and here is just an expectation, the real randomness comes from the sample. Okay? So what you can see is that Pn of f is a random variable which depends on the n samples, realizations. And on the other hand, what we want to compare it to is P of f. And P of f is not a random variable. It's just an expectation operator using the whole probability of x and y. So if we consider all possible functions f in this last class, we obtain something which is a set of random variables, Pn of f, indexed by functions. And this is called an empirical measure indexed by f. So there is a branch of mathematics which studies explicitly the convergence of Pf of f minus Pn of f. So this converges to 0 as the size of the sample grows. And this branch is known as empirical process theory. Okay? So here I've just, on the slides, those are just Wikipedia links that you can click on. But if you want to have an idea of what are the mathematical tools that we will use, basically we will use empirical process theory to compute such bounds. So I think this is it. Let me just simply give you one result before we move on to next week. So the true risk of G and the empirical risk of G end up being, if you just shift a few notations, the difference between the expectation of f of z and the mean of f of z computed on a sample. Okay? So this is a very, very classic problem in statistics. What is the gap that you can expect from the real expectation of something compared to the empirical expectation of something? Okay? So again, the reason why we said that the empirical risk converges to the true risk using the strong law of large numbers is the same idea that we can use here. We know that the expectation of something minus its empirical estimate converge to 0 in probability. That's the idea of the strong law of large numbers. But this is not enough. This is not enough because this just tells us that if you have 1 billion observations, then maybe this minus this will be small, but we don't know how small. So here is a very fundamental result, which we will, I will very briefly discuss the proof in the next session, but which was proved by Hovding in this form. If you assume that we have n random variables, z1 to zn, z1 to zn, and you assume that f of z is bounded between a and b, so here remember that in our case f of z is always either 0 or 1, so it's bounded, then the probability that the difference between the empirical estimate and the real expectation is bigger than epsilon is smaller than this quantity, which depends here on the number of points on the epsilon square. So compare this with this. Those are two completely different results. This is just a limit. It's completely useless. It doesn't tell you how fast this converges to this. Okay? If you assume now that this is valid, you get Hovding's theorem. Okay? So this Hovding's theorem will be the building block to start proving some of the bounds that I've mentioned. But just before I leave you, I really want you to look carefully at this. This is saying that the probability that the difference between the real expectation and what you compute using finite samples, the probability that this is bigger than epsilon is smaller than, so let's leave epsilon aside for a second and look at this. This is n. Basically, this says that the probability that this is big, if you want, decreases exponentially with the number of points n. So this is already telling you why it's not just the limit when n goes to infinity, but it's very important because the more n you have, the more points you have, basically, the faster, the smaller you can expect this gap to be, and this is in probability. And then the influence of epsilon we will discuss next time. So I will see you next time. I think you've all handed the homeworks. I will give you another homework this afternoon. I will put it on my website, and you will have 2 weeks to do it. It will be about regression, simple regression task. See you next week.